Welcome back to the online Graphs of Matroid seminar. Today, we're happy to have Relinde Jurrius from the Netherlands Defense Academy. So whenever you're ready, Relinde.
Thank you, Zach. It's always a pleasure to speak in this nice seminar, especially for us at the other side of the ocean. It's a very good way to keep up with what's happening in the Matroid world. So I'm happy to talk to you today about a construction of a derived Matroid, the combinatorial derived Matroid. And what I'm going to tell about that is, I will mainly focus on the first two parts that you see here on the list, and I will warn you that there will be a lot of hand waving. I will try to focus on the motivation for why do we study this object and some of the definitions where we encountered it before. And I will tell you what ideas there have been to construct a derived Matroid, and then propose a new one and explain why it has some nice properties. And I finish up with some open questions. Some of them are, how do they relate to the previous definitions? But it will be made clear, hopefully, why we tried something else. So for me, the motivation to study this structure actually comes from coding theory. So together with Ruud Pellikaan, who was my PhD supervisor, we were studying something. It had to do with decoding and coset leader weights. And a structure came up that we called the derived code. And it turns out that this was an instance of a problem that actually was around already since the 70s in various forms, and Henry Crapo and Giancarlo Rota, both more or less independently and also a bit the same, asked this question: what are we going to do? We're going to start with a Matroid, and we're going to make a new Matroid out of it that we call a derived Matroid. And the ground set of this derived Matroid are going to be formed by all the circuits of M, or all the co-circuits, and some natural definition of dependence between these circuits. So we're going to study dependencies between dependencies, or second-order syzygies, if you like that word. But that's a bit of the background. Well, where does it show up in coding theory? We were doing the following. So we start with a code, and for me, an NK code, it means a subspace, a k-dimensional subspace of an n-dimensional space. And this thing is generated by a k times n matrix. And this matrix also gives you a Matroid. So a code is basically a representation of a representable Matroid. Only coding theorists like to look at like the rows of the matrix instead of the columns, what Matroid theorists do. Well, for coding theory, sometimes you also do that because we're considering the projective system associated to this code. That means we take a generator matrix and we look at all the columns and we say, well, every column now are the coordinates of some projective point. And so I can associate to my code some points in space. Again, just like a representation of a representable Matroid. Now, what are we going to do with these points? We're going to look at every k-1 of them, and we're going to see if they span a hyperplane. And this is a hyperplane in the linear algebra sense, and not in a Matroid sense. And well, we just ignored if k-1 points span a space of a lower dimension. We are just interested in what are these hyperplanes doing. Maybe you have some multiplicities, we throw them out, and you end up with a hyperplane arrangement. And the derived code now is the code that is the code coming from this hyperplane arrangement. Basically, what you do is you take your hyperplane arrangement, you coordinatize your hyperplanes, and you put them in the columns of a matrix, and then you get another generator matrix of a code out of it. So let me explain this with an example. So here's our code. Or we can say it is a matroid on 4 elements of rank 3. And actually the 4 elements, they are the black dots that you see over here. Now, what are we going to do? The total rank of this matroid is 3. So we're going to look at every 2 points and see what hyperplane they span. Well, a hyperplane in this case is a line. So we're looking at all the lines that go through 2 of the points. And we simply take all tuples of points and then look at the line that's going through them. We coordinatize that line and we put it in a matrix. So for example, if I look at the first 2 points, so the point 1, 0, 0 and the point 0, 1, 0, the line that goes through that is, well, the vector orthogonal to both, and it's 0, 0, 1. And so you see, so for example, if these were the first 2 points, then this is going to be corresponding to the line going through them. And now we're going to study these lines as an arrangement, and that gives us a derived code. Now, there is something to note here, and that is that the derived code is not a Matroid invariant. And you can see that by this example. So on the left, on the left and the right, you see the same Matroid. And we take 6 points, 3 of them, and the other 3 are on the line, and the rest of it is, all the other 3 sets are independent. And what can happen geometrically is you're either in the situation on the left, so when these hyperplanes that are spanned by 2 points of my Matroid intersect in the same point, or they don't. And actually, when Ruud and I were working on this, we used the derived code to distinguish between codes. Because equivalent codes from a Matroid point of view can have different derived codes. But we were working with this and we said, well, okay, so can't we say something from a Matroid perspective? Because from a Matroid perspective, what do we kind of expect to happen? Well, we expect to be on the right-hand side. Because those 3 lines that we end up with, in general, 3 lines, we don't expect them to go through the same point. So we were thinking maybe we can do something in order to make like the most general option for this derived code. And that would then only depend on the underlying Matroid structure. And in order to do that, we looked a bit more on what's going on if you make this derived code. And that's actually the following. So from a lattice point of view, or from a geometric point of view, what do is you start with a code and you look at the geometric lattice associated to it. So you make as the points, you make the points in the code, and all your elements of the lattice are the flats. So this is the lattice of flats of the associated Matroid. Now, what do we do with this geometric lattice? We flip it upside down. So yeah, the hyperplanes become the points. And now you have to add some extra elements, because if you simply take a geometric lattice and flip it upside down, it's not geometric anymore in general. So you have to add a bit more elements to it in order to get a geometric lattice again. And we kind of want to say, well, we want to add as few points as possible to keep with this as general as possible idea. Now, this also works better with a picture. So here is the code and the derived arrangement, the derived code that we saw before. If you look at these 4 points, A, B, C, D, and the Matroids they give, then this is the lattice of flats of that Matroid. So every 2 points, they form a flat. And as soon as I have 3 of them, they actually span the whole space. Now, if I now instead want to consider the lines that are spanned by all those 2 points, I'm actually looking also at the hyperplanes of the Matroid, because the hyperplanes of the Matroids, so the ones over here, they're going to be the points in my new lattice, which is why I flip it upside down. And then I have to look at all, well, their intersections. And some of those intersections I already had, and some of them are new. Right? So these are those points A, E, F, G over here. And so actually what happens is you flip your lattice upside down and you have to add these 3 new points. And the other ones were things that already existed. Right? So for example, if I take 1, 2, 3, that means that the lines 1, 2, 3, so 1 is over here, and then 2 is over here, and 3 is over here. They go through the same point. But for example, 1 and 6, so that's a line over here and a line over here. They intersect in a point that wasn't in the Matroid before. So we have to add this extra element to it. And well, for a long time, I thought maybe I can just, write down what's going on here. Right? So I flip my lattice upside down, and then, well, I know that there are some, if I have a pair of flats that's not modular, then by flipping it upside down, this thing violates semi-modularity. So I kind of have to add an extra element in order to make that right. And I tried for a very long time to prove that this actually always works. And then I found out that it doesn't, because people already decided a name for this. So this geometric lattice flipping and adding construction, it already has a name, and it's called the adjoint of a lattice. And the good news is that every derived code, as we were studying it, gives an adjoint. But the bad news is that not every geometric lattice has an adjoint. In fact, it's a result from ages ago that the Vamos Matroid doesn't have one. And also, if it exists, it's not necessarily unique. And because this adjoint, because it comes from a derived code, it depends on the representation of your Matroid. Right? Different representations give different derived codes, and then also give different adjoints. Well, I only realized this years after I had given up on the problem. Looking back, I was slightly relieved that I wasn't too stupid to prove it, but that someone else already proved it's not possible. On the other hand, I did feel a bit stupid for not realizing that earlier. If I had just found the right paper with the right name, I could have saved myself a lot of trouble. This is actually how I came interested in this. And I'm now going to give another part of the motivation of the derived Matroid that was done in an independent course, and which is also how I got involved in it again. So this is mainly based on the work of Oxley and Wang, who started out with Longyear. So Longyear did the binary version, and it was generalized by Oxley and Wang to codes over general fields, or actually Matroids with a representation. But for me, that's the same as a code. And what did they do? Well, they started with a code. And it's a well-known thing that if you look at the supports of words in a code, that means, remember, my code was a k times n matrix, and I'm looking at elements in the row space. These are the words. And now I'm not looking at the words in the row space, but in the null space. And I call that the dual code. Well, if I now have a word in the dual code and I look at all its non-zero entries, everything that's non-zero, I call that the support of that word. These non-zero entries, they give me a dependence relation between the corresponding columns of the matrix we started with. So that means that in order for the columns of my code to be dependent, it means that there is a vector that I can multiply with this matrix that gives me the coefficients of the dependence relation between the columns. And this correspondence between the support of words in the dual code and dependent sets of the Matroid that's represented by this code, it's a well-known thing. And actually another well-known thing, and you have to think about that a little bit more, is that my dual code is actually generated by words of minimal support. So it's generated by things that we call circuit vectors. So circuit vectors are simply vectors that give me like the coefficients of the linear dependence of a circuit. And so I have a representable matroid. I know that certain columns form a circuit. That means there is a linear combination of them that adds to 0. And if I take like the vector that I have to multiply my matrix with in order to get exactly that linear combination, that's what I call a circuit vector. And circuit vectors, they span everything in your dual code. So if I take linear combinations of them, I get again more the support of these things will be dependent sets in the matroid. And now what are we going to do? Well, remember that the idea of the derived matroid was to do dependencies between dependencies. And now we have made a circuit into a vector, and we can just take the dependencies between these vectors, well, as linear dependence between vectors works. What you actually do is you start with a code, you look at the whole null space of this code, you take the things of minimal support out of that, and those, well, I take like as columns of a new matrix, and that's a representation of another matroid, and that's what we call the derived matroid. And we denote it with delta of OW, well, to show that it's the Oxley and Wang construction. And yeah, so in fact, this construction, I think it feels a bit more natural. You don't have to do all these geometry things with the lines and the points and the arrangements and stuff like that. But what happens underneath is that this is actually the same construction as the derived code. Up to duality, because what the derived code does is it's going to look at hyperplanes and dependencies between them. And we all know that hyperplanes are in one-to-one correspondence with co-circuits. And so the derived code looks at dependencies between co-circuits, and this derived matroid of Oxley and Wang, it looks at dependencies between circuits. The bad news is that both constructions, they depend on the representation. So first of all, it's not unique. And also, if you have an arbitrarily matroid, it doesn't exist, right? And so our goal was to find some notion of a derived matroid that works for any matroid. And in order to do that, we're going to study a bit more the construction of Oxley and Wang, because if you look a bit closely, then the following is happening. So here's an example of some circuit vectors I have, and I have crossed out where they have their support. And now I'm going to ask myself, well, is this thing going to be dependent or not? Well, we're not really sure, but we do know that the rank of the space these circuit vectors span, it can never be higher than the dimension of the space spanned by all the vectors that whose support is contained in, well, some column that has a cross here as well. So here I have 8 elements. 2 of them don't appear in the question. If I take like my dual code, that's where these things live, and I ignore these things that have zeros anyway, I can say, well, I just remove those 2 positions from the equation, and I look at the maximal dimension of what is left. Well, in the maximal dimension of what is left, it's actually the nullity of the non-zero positions, but in the normal matroid, in a normal code. So it follows in words, and it's it's a bit long thing in words, that if we have more circuit vectors in a set than the dimension of this code restricted to the unions of the support of the circuit vectors. So in this example, like this 6 columns, then we already know, I mean, if I have more circuit vectors than the dimension of something it's contained in, then these things are dependent. And if you translate that back, you see that a set of circuits is dependent if it holds that, well, I take all these circuits. It's a bit annoying, C is a circuit now, bad notation, sorry about that. If I take all these circuits and I take the union of their supports and I take the nullity of that set, if the number of vectors is strictly bigger than that, then we know that this set of circuits is going to be dependent. And this is a very important observation because it doesn't depend on your representation, right? So this nullity here, I mean, however I represent my Matroid, it will always work like that. And and this inequality is actually what we use to build our definition on. Because we know that, well, we sort of want all set of circuits that have this property, those we really want to be that they are dependent in the derived Matroid. So the hand-waving definition, or the idea behind our definition of what we call a combinatorial derived Matroid is the following. This condition that I just showed on the nullity, it gives me a family of sets of circuits, and we call them necessarily dependent. I mean, we know these will have to be dependent. But the thing is, it's not enough to just take these sets. You don't end up with a Matroid. So what do? Well, you sort of add some things to it in order for it to satisfy the Matroid axioms. How do we do that? Well, we have a good look at the dependence axioms. We make kind of operations on them. And then we take this family of necessarily dependent sets and we close it under these dependence operations. And so our idea is some things always have to be dependent, and then we kind of close them under the dependence axioms. I don't know if you hear that, but my cat agrees. So for those of you who are not fluent in all axioms, here are the axioms for dependent sets. Now we can completely define a Matroid by its dependent sets. Well, the first one is just that the empty set shouldn't be dependent because then boring things happen. The second one says that all supersets of a dependent set are dependent. So if I have a dependent set, then everything that contains the dependent set should also be dependent. And the third one says that if I have two dependent sets and their intersection is not dependent, then what can I do? I take their union and I pick out one element from the intersection. And this thing should also be dependent. And that holds for everything of the intersection that I can put out. And you see already from how these things are written, like from an if-then, how operations come from it. Because basically what we're going to do is we're going to say, well, we have all these sets that we know have to be dependent. And we just say, well, if we find one, we just throw in all its supersets because we know by this if-then construction that they have to be dependent. And also if we find two dependent sets somewhere in our necessarily dependent family and their intersection is not there, then what do? Well, we take their union and we throw out something in the intersection, and everything that we can make in that way also will be dependent. So in formulas, these are the two operations that we do. So we take the set of circuits of some matroid, and we take a subset of all, I think this should be a subset of the subsets of C, actually, because A is going to be a family of subsets of C. So this thing here is not completely correct. And what do? We define the operations epsilon and arrow up. And what do? Well, what does epsilon do? It keeps all the sets you already have. And it says, well, suppose I have an A1 and an A2 that are already in my A, and their intersection is not in A. Then what I'm going to do is I take their union and I throw out some element that is in their intersection. And I do this actually for all the elements in their intersection. So for A1 and A2, I'm going to add a lot of things to my curly A. Namely, I just glue them together and I pick out an element in the intersection. Then I glue them together, pick out another element from their intersection, and I do this for all the elements in the intersection. So this thing is going to give us a lot more dependent sets. And also the upward arrow just means for every set that you have all the supersets, throw them in as well. So you should see these two operations as closing under the third and closing under the second dependence axiom. Now that we know that, we're just going to repeatedly do this until the process stops at some point. And because everything is finite, it will stop at some point. We just hope that it doesn't stop at having everything. But in fact, you can show that sets will only get bigger, right? Maybe they stay the same size, but since what you can do is you add supersets, well, and they are bigger. And since you take unions, and okay, you take one element out, but it also more or less gets bigger. So that means that if small sets weren't already in the thing you started with, they will also not be added. Here is the formal definition. So I take a Matroid and I take its collection of circuits. And now I'm going to define a collection A node. And curly A node, it is all these necessarily dependent sets. So that's all the sets that satisfy this nullity condition. So what I do is I take my set A, it's a set of circuits. I take the union of the supports of all these circuits. I calculate the nullity of that. And if that's strictly smaller than the size of my set, then this thing has to be independent. And I put it in A naught, which is my definitely dependent pile. And now what we're going to do, we're going to inductively define A1, A2, A3, etc. by all the time first doing this operation epsilon on everything. And so we're going to check for which pairs is the intersection not in AI. And if it's not, then we're going to add the union minus something in the intersection. And if we've done that, we're going to add supersets of everything if we didn't have them already. And in the end, what we say is our curly A is going to be the union of all these AIs. And in fact, it's going to be the last one because you're only going to, because you never throw things out. You only put things back in. You only put extra things in. And so our derived Matroid is going to be, its elements are going to be the circuits of the original Matroid. And the dependent sets are going to be this curly A. So the necessarily dependent sets, and then we close it under these two operations. Now, of course, you have to prove that this is a Matroid, but the good news is that you can just check the dependence axioms, and these things are built to satisfy the dependence axioms. So there is a bit of subtlety involved in the thing that what you do is you take this epsilon and then you have something that's closed like under axiom number 3, and then you do this thing to close it under number 2, but then you have to check again that you have to do epsilon again because there's all these bigger sets that you didn't involve in this closure again. But you can actually prove that you can first do this epsilon all the time and then close one time at the end to get to A. And so we do have some kind of a grasp on what's going on here. And then in the end, you prove that this is a matroid by just a few lines of checking all the dependence axioms. So this is good news because now we have a definition of a derived matroid that starts like from the same idea as that we already found in the other definitions. And moreover, this is going to work for every matroid, right? Because the only thing you need to know is this nullity function and the size, and representations or things, they don't play any role in this thing. So to give you an example for the Vamos matroid, it didn't have anything derived in all the other definitions. It doesn't have an adjoint, and since it's not representable, it also doesn't have the Oxley-Wang construction. And well, first of all, this thing already has 41 points because the Vamos matroid has 41 circuits. So if you want to do any calculation from this thing, it blows up really, really, really fast. And what we can do is we can take two sets of circuits. We know in the Vamos matroid, these planes that are made here are the only 4-element circuits. And if I let A1, I take like the upper 3 planes, and for A2, I take the lower 3 planes. These are both dependent. And by looking at the picture, you say these planes, they kind of form a cycle, so I would like them to be dependent. This is the most hand waving that it will got, but we can actually check this. Because if you look at like the upper 3 planes, then its support has size 6. So G and H are not in the joint support of these 4 things. And let me just go back to the definition here. What do we have to do? We have to calculate the nullity of like this other 6 points. And well, what is the nullity? The rank of this thing is 3. No, it's 4. It spans everything. So the nullity is 6 times 4 is 2, and we have 3 planes. And 3 is bigger than 2, and so that means that this is dependent. And exactly the same thing holds for the lower triangle. And now you also see why we need this whole closing business. Because what can we do? We can say, well, now I'm going to glue A1 and A2 together because their intersection is not something dependent, and because their intersection consists only of this plane ABCD, well, which is just a single one, so it's not going to violate this nullity condition. So that means that we are allowed to take the union of A1 and A2 and picking out something in their intersection. Well, there's just one thing that we can pick out. And this A3, it consists of like the outer 4 planes. And these outer 4 planes, this set will now also be dependent. And actually it's in curly A1, but not in curly A2, because it's really made by this operation epsilon. And also, I mean, again, if you look at the picture, I have like two circuits and I put them together. And if I take the middle out, then these 4 planes, they still feel like they're like in a cycle. So our intuition just from looking at this picture is okay. So yeah, for the Vamos Matroid, you can do some things like this. But as I mentioned, it becomes big very fast. So a lot of things we can't answer for it. So here are like the main properties that we actually proved about our new construction of the combinatorial derived Matroid. First of all, you can find a cryptomorphic definition by using its circuits. And then what you do is you start again with this necessarily dependent sets, but then you only take the inclusion minimal of those. You do your operation epsilon. Again, you take the inclusion minimal of those. You do your epsilon operation. And at some point, this will also converge. And then you're left with the circuits of your combinatorial derived Matroid. And you can kind of prove that this gives you the same thing as doing this construction of finding all the dependent sets and I'll simply take the minimum over there. Furthermore, we've proven that the combinatorial derived Matroid is connected even only if the Matroid itself is connected. Well, this is not a surprise, but it's always good to check these things. We have a very cute proof that sort of uses base exchange to make sure that you're never out of your connected component. And finally, a nice property, which is nice but also not so nice, is that the rank is at most the nullity of your Matroid, so the size of E minus the rank of M. And this is an upper bound. And we are kind of sad about that because we believed for a while that we could prove that it's actually equal to this number, which would be nice because this derived code and the adjoint and the Oxley-Wang construction, they all make derived Matroids that have like the largest rank possible, which is the size of E minus the rank of M. But we didn't manage to prove that this is actually an equality. And we're also kind of undecided on whether or not it is. Because, well, if it is, then it should have a lot of properties that the previous definition also had, but it clearly hasn't all the time. And if you try, for example, our friend the Vamos Matroid, we don't know what its rank is. We don't know if it's 4 or 3. We know that it's not 2. I mean, that's like really too small. But if it's 4 or 3, we don't know. And doing this iterative process with all the dependent spaces, I mean, there's literally thousands of them. So, well, we couldn't get the calculation go to work. So even for like the smallest example that gives us actually something new, we don't know what's going on. So that's actually also one of the open questions that I didn't put here, but of course it is one. So a main open question is that, can we actually say something about this rank? And something that's related to that question is can we classify what are the independent sets or the bases or the dependent sets or the circuits or the flats or the whatevers of this combinatorial derived Matroid without doing this whole iterative construction? Because the good thing is that it works. The bad thing is that's impossible to calculate with, right? We would kind of want to have a result that says, well, if your set looks like this, then it's always independent. I mean, we have a result that says if your set satisfies the nullity condition, then it's dependent. But we don't have a similar result for independence, which would be really nice because then you can maybe, see what is your minimal rank. We were a bit on our way with that, but it's way more complicated than we hoped. And some of the things that we hoped were true were violated by the Vamos Matroid. So we don't really know how that works. And also, we want to answer this question because if we want to relate our definition to the previous definitions, then, for example, if you want to say something about the adjoint, you kind of need to know what are the flats in our combinatorial derived Matroid. And at the moment, we have no idea. We can make the dependent sets and we can, we know that we can derive the flats from here, from there, but how they look, like completely open. So if you don't know, where your flats are, then it's very difficult to say something about your lattice of flats. So we believe that this is a step towards answering a lot of other more open questions. So I talked already a bit about saying that we expect our combinatorial derived matrix to be like the most general option, right? We know that we have some dependencies, and we want to, we know that we should add some dependencies, but we only want to add those that are given by the axioms and not more, right? So you don't want to overdo it. And so to say that it is like as like it's as independent as possible is saying we're going to use the weak ordering on Matroids, and we kind of want to say that this is I always forget what it is. Is it the biggest? If it's the most general in the weak order, I think it's like the biggest of all possible derived matroids. Yeah, thanks. So we have some small results towards saying that. For example, it can happen that our combinatorial derived matroid, that we don't need to do all this business with closing under the dependence axioms, because the things that have to be dependent, they are already closed. And so you have to do like none of the steps, because they are not going to give you something new independent. And that's very nice, because then you know exactly how all the dependent sets look, because they all satisfy this nullity condition, and then you can calculate with them. And also you can compare them easier to the other existing definitions. But we're still unsure about how that works in general. And the final thing is, we would like that if our dual matroid has an adjoint, is our combinatorial derived matroid then isomorphic to one of these adjoints? Also, that we don't know. And for that, as I said before, we really need to have a better grip on the flats, because we can't really start saying anything about the lattice of flats if we don't have a clearer formulation of the flats or the rank or something close to that. So, all in all, there are a lot of things to do. We had this new definition. We were at first more enthusiastic about it than later on, because some of our proofs turned out to be not completely true. But that does mean that there are a lot of things to do, and where this whole definition sits, like within the rest of the definitions, I think there is a lot of work to do. And so, if you like doing that, then get in touch and see if you can work with us on that. And I think that's all I wanted to say, and thanks for your attention.
Okay, on the count of three, let's all unmute and give Relinde a round of applause. 1, 2, 3.
Thank you.
And are there any questions?
Yeah, I just had a quick question about so when you got the third dependence axiom, yes, there are two choices, right? When you're choosing to make all of the things outside dependent, but there's also the intersection.
Yeah, so let me get back to that, because you have this if-then construction, right? And there's actually two things to make this happen. You can say, well, if I have that this intersection is not in there, then I do that. Or you can say, well, every time I have two things, then I'm just going to put their intersection also in there, so that this first part of the if statement never happens and I don't have to worry about the second one. But it appears that this is going to give you boring matroids a lot of the time. because
Yeah,
then
I would
you're going to
do that.
intersect everything. And well, our feeling that we want things like as independent as possible is kind of counterintuitive with that. But you're right, there is a choice here, and we picked the choice that we thought would get us the most interesting Matroids. Because all these intersections, I don't think we actually worked it out with an example, but well, I think you can see happening that, you know, your rank will go quite low and a lot of things will be independent.
I mean, you wouldn't want to do the same thing. You wouldn't want to do the intersection all the time. That would be a bad idea.
Yeah.
But there is,
yeah.
but there might be interesting Matroids you get by doing.
By doing it by doing sometimes the one thing and sometimes the other.
I don't know. It's not really a unique solution, is what I was pointing out.
Yeah. So the thing is that it is unique as soon as you stick with these two operations that we made. So we showed a lot of things that, you know, the order doesn't really matter, right? So you can do a lot of epsilons and then close it upwards one time, and you end up with the same thing as if you would do it all the time in between. But yeah, I think it would also be difficult to like really point down what's gonna go on if you sometimes use like your epsilon operation on two of these dependent sets whose intersection is not yet dependent, and sometimes you say, well, I just make the intersection dependent. I mean, you would have to make precise when you're going to pick what, right?
Yep.
And
I don't have a proposal for it.
yeah, no, me neither, but I'm open to suggestions.
Any other questions?
Sure, I've got one here. Again, just on rule D3 here, because it has this negative hypothesis, you could have a case where after a couple of steps, you'll realize that something you did on an earlier stage isn't really necessary anymore, because this thing that wasn't dependent when you looked at this rule, well, now it's dependent. And so all those things you added weren't really necessary. Is there any way to kind of go back and take things out that you find aren't necessary?
Yeah, well, the thing is that's not going to happen because your sets will always get bigger. So the thing is that, well, I mean, there is some technicality involved, especially for smaller sets. But if you look at what's going on, then this D1 union D2 minus one element, most of the times it's much bigger than D1 and then D2, and especially bigger than also D1 and D2. Well, okay, that's clear, of course, but that means that if you would just do this like for all the minimal sets, and then you get some extra things, you take the inclusion minimal once again, and if you keep doing that, then you really just get the circuits, and it will kind of never happen that at one point you say, oh well, this intersection was not in D and so I had to add that, and that later on this intersection is again added back to D, because that would mean that well, there are smaller sets that would take care of putting this thing inside the dependence, and then well, you can kind of show that then you didn't really have to consider this huge D1 and D2 if it could have happened on a lower level. Does that make sense? Yeah, I guess the short answer is you don't get that because the sets you add are getting bigger and bigger and bigger. So you won't accidentally add the intersection of two things because it's too small.
Any other questions? So I maybe have a question. So if you take a Matroid M and delete some element E, do you know what happens to the derived matroid?
That's a very good question.
I imagine it would be a restriction. The new derived matroid would be a restriction of the old one, I would hope, but maybe that's hard to prove with the iterative definition.
Yeah. Yeah, I intuitively, I think you might be right. I mean, we do have this this result on the connectivity, right? So we can kind of assume that we are in a connected component, and then I think you can. Well, so if I take out an element in M, then it means that for my circuits, I'm also going. I mean, I'm in a derived matrix. I'm not losing 1 point. I could lose more than one. Right, I'm actually losing all the circuits that contain E, and yeah, so the dependencies between everything that's left, you kind of hope that it stays the same. Yeah. So I would expect this to be true. We didn't look at it, but I think it's true. It will be. So from this iterative definition, it might be difficult to prove, but as I mentioned, you can also like really just look at the circuits by, you know, taking inclusion minimal sets, doing this D3, going back to the minimal inclusion sets, etc. And I think maybe there you can show what's going on. But it's a nice question. I'll pass it on.
Sounds good. Okay, any other questions? Okay, so maybe I'll stop the recording and we can continue the discussion off the air.